Hi, my name is Nicola Paone, and I'm a professor of measurement science at the University Polytechnic delle Marche in Italy. I will talk today about the role of measurement in zero-defect manufacturing and its importance. Actually, we are fully aware of this, and we are working at these topics within the openZDM project, which is financed by the European Commission within Horizon Europe framework program. So which are the contents of my talk today? First of all, I want to introduce the concept of digital factories and the role of inline quality control in these environments. Then I will say some words about NDIs, non-destructive inspection systems. Then I will talk about the model of a measurement system in order to introduce uncertainty and the role of uncertainty in conformity assessment. Finally, I will say something about measurement system analysis, which is so important to be performed in order to assess if a measurement is fit for the scope. Let's go to the role of inline quality control in digital factories. Why quality control in production lines is so important? Well, because quality control means to verify compliance of within specifications of something that you are observing. This means that you have to measure something and to perform conformity assessment. And this is important for the process, for the production process, in particular to improve production efficiency and process efficacy through the early detection of defects. And then this is also important if you look on the left for the customer, because customer satisfaction depends on the quality of your production and also on the cost of the warranty policies that you are obliged to apply to your products, and which will determine costs if the quality is not fit for the scope. This means that today, most production factories are going to 100% product or component testing. This means that in the lines, you measure many quantities, and you measure specific features, and you perform functional tests. And these things are important to be done in line, and this implies the use and the availability of quality control stations on the production lines. Let's have a look at a typical three-layer architecture of a manufacturing system. The one represented in this slide on the right comes from the Goodman project, which was one of my past projects within Horizon 2020. Three layers. The bottom layer is the shop floor. Here you have the machines, the operators. Here you have the real production taking place. We have here the measurement systems, and here you have most of the problems related to production. Here you take measurements, and when you send the data, you send data to the upper layer, the third layer on top, where usually it is performed data analytics and knowledge management. What is the intermediate layer necessary for? Well, because you will not send all the data you acquire from the shop floor to the processing layers, and therefore you need some sort of pre-processing of the data before being analyzed. And the same applies from the management actions that you decide at the third level. You need to process them in order to transform them into set points to the controllers acting on the machines in the shop floor. All this picture tells a lot about what is zero defect manufacturing. Today, zero defect manufacturing is the most advanced approach to quality control in manufacturing. Zero defect manufacturing actually requires massive amount of data, very large amount of data, which are acquired from all processes and from all products and components flowing through the line. And it enables process and quality control, actually at local level, which means at single process level, but even at factory level, global level. In these environments, once data are collected and available, then data analytics enable early detection of patterns, trends in the process and product quality. Then modeling the production process is made possible by the availability of data. Data models you can build, digital twins can be validated. And then management of production through preventive and or corrective actions can effectively take place. So quality of the data is important because if you use data to make all these decisions, then the quality of your decisions will depend on the quality of the data. Actually, we measure to take decisions, always. And most quantitative data originate from measurements. Measuring instruments, unfortunately, due to their nature, to their complex interaction with the measurement, and also to the complexity of the environment where you have noise, disturbances, produce data that are always intrinsically affected by uncertainty. Therefore, the uncertainty of measurement affects also the level of confidence in the decisions that are made on the basis of uncertain data. Basically, the scheme on the right tells very simply that the quality of the data has an influence on the confidence level on the following decisions. It is therefore essential to guarantee that the quality of the data is fit for the scope. And in order to do that, you need to be able to understand and manage the entire measurement process. The second topic I want to talk is NDIs. What is a non-destructive inspection system? In reality, non-destructive inspection systems can be considered to any extent cyber-physical systems. They include hardware and software. Their essential features is that they perform non-destructive tests. This means that the system must perform measurements usually without any contact with the object of measurement. And then they perform inspections. This implies that at least one measurement is done within an NDI. Usually more sensors are present in an NDI, and these are used to determine the quantitative value of at least one characteristic parameter that is subject to the specifications. Therefore, any NDI comprises at least one measurement system capable of taking measurements in a non-destructive way. But not only measurements are done into an NDI. Actually, you need hardware elements to perform measurements, and they produce the raw data. But then you always need one or more actuators of different technologies, and they are in charge of executing the test sequence. For example, place the product in front of the sensor and remove it after the test. But then you also need the data acquisition electronics, and usually a processing unit, generally a computer. Then you're connected to the factory network and you send data. There are also software elements for software control and management to manage the test sequence, to perform data processing within the NDI, and this is usually done to extract characteristic features, and then eventually conformity assessment and diagnosis can be performed on board of an NDI, as well as classification of defects. We are talking about measurement. What is a model of a measurement system? Well, it is represented here on the right. It is a system which receives an input Qi, which is the quantity you need to measure, the quantity you want to observe, the measurand. And this instrument provides an output, usually a signal, usually an electric signal or a digital number, which should be a function of Qi. When using a measurement instrument, the receiver, the observer, will get the output. The output quantity will then be useful in order to compute the input quantity by inverting the model of the measurement system. And how do you get the model? Well, the model of the measurement system is usually obtained through calibration. This is an example of calibration of a pressure sensor. In the abscissa, you have known reference values of pressure. In the ordinator, you get the electric output. You collect a number of observations, and you perform a regression analysis. This is, for example, with a straight line. And this linear regression analysis provides the function f. However, we know that, and we said that uncertainty affects any measurement. Therefore, the real model of a measurement system should include also the effect of disturbances. And on the instrument, always you have many and uncontrolled and unpredictable disturbances affecting the measurement. What are disturbances? Temperature variations, vibrations, electromagnetic disturbances, and so and so and so. What do they do? Well, they may modify the function, and they are called modifying inputs, or they may be adding to the output and therefore causing interferences. And all this happens in a random and systematic way. Well, this needs to be understood. And actually, the uncertainty should be estimated before performing any conformity assessment with that measurement instrument. And so how to evaluate uncertainty? The ISO guide to the expression of uncertainty in measurement provides you the answer. There are several methods. The first one is to use statistical methods, the so-called type A method. It means that if you can, repeat n times the measurement of the same quantity, and then use as a result the mean, the arithmetic mean. Because the arithmetic mean will be the best estimate of the measurement. However, this is applicable only if the quantity that you are observing is stationary, or in some cases periodic if you face with the periodicity. And this is sometimes not the case. And also in many industrial situations, there's no time to perform n measurements. Therefore, often you deal with only one measurement. However, the distribution of the repeated observation allows you to perform the estimate of uncertainty. The ISO guide suggests you to compute the standard deviation with the typical expression reported here. And then use the standard deviation divided by the square root of n and apply this as the uncertainty of the mean that you are estimating. Of course, if you're performing only one measurement, the uncertainty of the mean coincides with the standard deviation. And the mean itself coincides with the only reading you have. Then the GUM, the guide, proposes you to use a larger interval to express your uncertainty. It tells you to use expanded uncertainty U capital, which is k times the standard uncertainty U. K usually is fixed to be equal to 2 in order to reach a 95% confidence level in the case of Gaussian distribution, which is random variances of your readings. There exist also other types of methods to estimate uncertainty, which are called type B. I will not go through all of them, but most of them are model-based, or they are Monte Carlo simulations, and so and so and so. You can find a lot of literature about this. However, using either type A or type B approaches, you can get an estimate of expanded uncertainty U capital. And no matter how uncertainty is evaluated, your result of a measurement will not be a number with a unit, but will be an interval of amplitude plus or minus capital U. This is very important. One measurement and you get an interval, not a single value of the datum you're searching for. This has an effect if you use these results in conformity assessment. If we look at these two pictures, we see two examples. On the left, the instrument has an uncertainty U sub L, which is rather large because the distribution has a large horizontal amplitude. In the second example on the right, the uncertainty is much smaller. The distribution is smaller in amplitude. Both instruments perform the same measurement of the quantity x1. However, if the measurement is done with the instrument on the left, part of the distribution of the possible output of the possible values corresponding to that output of the instrument x1, part of that distribution will fall beyond the specification limits. These two red lines represent the lower and the upper limit of specifications. It is the range within x should fall in order to verify conformity. However, if there is a non-negligible probability that you read X1, but the result could be out or vice versa, you have a probability of wrong diagnosis. For example, this is a false negative if the reality falls beyond the upper limit, because your conclusion reading X1 would be that the product that you are examining is compliant to the specifications. So it is a negative in terms of diagnosis. However, if the reality is beyond the specification, this would be a false negative, a very bad diagnosis. Of course, on the right, you see that if the instrument distribution, if the instrument uncertainty is much smaller, the probability of wrong diagnosis drops to be negligible. This comes to the first important message. After evaluating uncertainty, you have to estimate the uncertainty to tolerance ratio. And if the uncertainty to tolerance ratio is small, your instrument is fit for the scope. If not, you have a problem. An example is provided by this standard. It is a standard on geometrical product specifications. In particular, it tells about decision rules for verifying conformity or non-conformity with specifications. It is written for geometrical quantities, but actually the content of it can be largely applied also when you measure other quantities. So let's consider it as a general example. What it tells, you have a certain specification range, your tolerance interval. However, it tells if you want to verify conformity, do conformity assessment within a smaller interval, which is called the conformity range. Smaller by 2 times U capital. So you deduct from the specification range 2 times U. Why? Because these green intervals, if the reading would fall into these 2 green intervals, having amplitude 2U, you would be in an ambiguous region, because the measurements falling here could be in reality measurements which were falling beyond to the right of the upper specification or below the lower specification. And therefore, you are in a risky region. If you want to perform a safe conformity range and conclude that your measurement is falling within the specifications, reduce the specification range to the conformity range. And this means that if you don't want to lose too much of your ranges, the uncertainty to tolerance ratio should be small. Should not exceed 1/5, but better 1/10. And this is a very important message. Your instrument should have an uncertainty fit for the scope, much smaller, 1/10 of the specification range. And this leads me to the last chapter of this brief webinar, measurement system analysis. What is this? It is an experimental methodology used to assess if a measurement instrument is fit for the scope, and if it is fit for the scope in industrial conformity assessment. It allows you also to identify sources of uncertainty, in particular to attribute part of the uncertainty to the operators when they're using instruments. Actually, MSA is composed of 2 sets of instruments, gauge capacity indices, CG and CGK, and repeatability and reproducibility analysis, the so-called R&R analysis. What are gauge capacity indices? Well, these things are very well understood by people familiar with statistical process control, because gauge capacity indices are built in full analogy to process capability indices CP and CPK. These indices, CG and CGK, for gauges, are defined to estimate gauge capability to perform a measurement task when used in conformity assessment. They compare the uncertainty interval U to the tolerance T. In particular, they compare the ambiguity intervals to the tolerance T. And they consider that the ambiguity intervals are ample 2 times U capital, 2 times the expanded uncertainty. That is, 4 times the standard deviation of your readings. CG is defined here. It is 20% of the tolerance, 1/5, divided 6 times the standard deviation. 6 times the standard deviation is 1.5 times the ambiguity interval. When CG is equal to 1, you are at the bare minimum. And actually, if you prescribe that your ambiguity interval to the tolerance has a ratio of 1 to 10, this will immediately lead through this formula to have the requirement that CG is larger than 1.33. Similar considerations apply to CGK. However, CGK tells you also something about the fact that the reading is centered or not within the specification range. So the two together, which both should fall in the range of more than 1.33, allow you to understand if your instrument is fit for the scope. Measurement system analysis includes also repeatability and reproducibility tests. These are methods to verify the system ability to reproduce measurements on different samples with different operators at different times. But what is repeatability? Repeatability is the variation of the measurements taken by a single operator using a single instrument on the same part and under the same conditions. While reproducibility is the variation of the measurements taken by different operators or different instruments or different laboratories on the same path. And a gauge R&R study involves the measurement of a predefined number of samples. Standards suggest at least 10 of the same object, of the same code, carried out by different operators, at least 3, and each operator must carry out a certain number of repetitions, at least 3. So let's take 10 samples, 3 operators, 3 measurements repeated 3 times, at least 90 measurements repeated. Then what you have to compute? You have to compute this expression. Gauge R&R is a percentage. And is the square root of equipment variability, EV squared, plus appraiser variability, AV squared. What are EV and AV? EV, equipment variability, is an estimate of repeatability, which is made using ranges instead of standard deviations. We don't use standard deviations because, however, these estimates are done on a low number of data. Appraiser variability, this is an estimate of reproducibility and accounts for operators. Let's look at the expressions without going into depth, but you can study them in detail if you like. Equipment variability is the result of processing the repeated measurements that you have done. You have measured x sub I j k, where I is the index of the operator for 1 to n. J is the index of the measured sample for 1 to p. K is the index of the repetitions that you are doing, 1 to r. What you estimate are mean and ranges. Mean and repeatability of each operator I on each sample j. Mean and repeatability of each operator I on all the samples, and then the overall mean and repeatability on all the data. Computing all these quantities allow you to estimate equipment variability. With this expression, and K1 in this expression is a statistic coefficient depending on the number of data collected, which is depending on the number of operators, samples, and repetitions. Then you need also to compute appraiser variability. Is the variation between appraisers, between operators. It is the variation in the average of the measurements by different appraisers when measuring the same characteristic on the same path. It means that different operators may use differently the instrument. It is computed by this expression, which again I go quickly over, in which you have x sub diff, which is the difference between the maximum appraiser average and the minimum appraiser average, because each appraiser may perform measurements with different averages. And then K2 is again a statistic coefficient depending on the number of data collected. At the end, if you have EV and AV, you compute gauge RR with RNR with this expression, and it is a percentage. Well, if this percentage gauge RNR is below 10%, you are good. Your measurement is fit for the scope. If you lie in the range 10 to 30%, it may be acceptable, but better to improve. It may be acceptable depending on the application, not on demanding applications. In any case, above 30%, this is not acceptable. So, what is the lesson learned? Well, my concluding remarks are measurement instruments and more in general NDIs are more and more used in line. And inline quality control implies the use of quantitative data. Quantitative data originate from measurement. So when using any measurement instrument, always take into account uncertainty. Calibrate your instruments, estimate your uncertainty, and then check instrument performance when in use. And for doing this, use MSA methods. Therefore, estimate gauge capability indices and perform tests for repeatability and reproducibility. So what is the lesson to be taken home today? Well, estimate uncertainty of your measurement, and in zero defect manufacturing, always use data you can trust on. Discard the others. So I thank you for your attention, and I introduce you briefly the consortium being part of the openZDM project. And if you want to contact me, this is my address and this is my email. So thank you very much, and bye-bye. Ciao.